So now we're going to talk about a very important concept when it comes to quantum technology in general, and it's the idea of Rabi oscillations. So right here I have a diagram of our quantum system, in this case related to our electron that we had in our NV center. Our electron can be in a number of different states, pointing in different directions that correspond to that state, and we need a way to be able to control what the configuration of our electron is in. So let's say our electron starts pointing in this direction, and we'd like to get it to point in the opposite direction down here. How are we able to control this? Well, first, we have to energize our system so that we can get this to be in a metastable configuration. Basically, we want this to be like a rock that's teetering on the top of a cliff, so when we give it a little push, it'll start to roll down. And we do that by applying this constant magnetic field over here, this B sub Z. Now that we have this constant magnetic field, our electron is ready with just a little bit of a push to start processing or rotating about the Z-axis. We can control how much our magnetic spin of our electron processes by applying a specific pulse of electromagnetic energy, like a certain microwave signal. And that pulse is determined by the Rabi frequency of our system. So, once we know that Rabi frequency, we can apply just a sliver of that pulse by controlling the amount of time that we send the pulse at our system to get it to rotate for only a fraction of the circle. So, if we apply that pulse for a certain amount of time to rotate halfway between its starting location and the end, we can call that a pi over 2 pulse. So now that we've applied our pi over 2 pulse, our qubit is pointing in this direction, which is 90 degrees from where we started. So, as we continue on, rotating from this point, we get down to the bottom at our full pi pulse, where again, looking at our graph, we're at the bottom of the throw, and it gets more difficult to tell between our original Z state. Whereas if we continue to rotate here to 3 pi over 2, we again are at the top of our trough. So one thing to notice with this graph is that as we go on, it starts to attenuate. The signal that we get out is not as strong the longer that we continue this experiment. And that has to do with a concept that we know as decoherence. Essentially, the longer that we run the experiment, the more energy or information that we lose to the environment. That energy can be lost to interactions with other lattice sites in our diamond. It can be lost due to interference from other electrons in our ensemble. Anywhere where our system is interacting with anything else in the universe can bleed off information from our system and cause it to lose the particular quantum state that we've put it into. This is one of the chief challenges in all of quantum technology, and one of the main hurdles to overcome in order to make quantum sensing and quantum computing a viable technology for the future.
In the previous experiment, we calibrated the microwave field, and in this experiment, we're going to vary the microwave pulse length and amplitude in order to find the most optimal pulse parameters. So in order to set up the Rabi oscillation experiment, we're going to first change our frequency to 2.705, which is in accordance with the magnetic field that we have set. So if we want to sweep through any of the parameters like the pulse length or pulse duration, then we go to the interlace script and load the parameters depending on the experiment we want to do. Once the experiment is running, then we go to real-time processing. So this is the Rabi oscillation that we would expect to see.
I want to say a big thanks to QuantCAD for sponsoring this video and letting us use their facility. More in the description below.